So today's lecture is on design of post-tension pre-stressed concrete bridge. And the data given are: the cleared span is given 10 meter, the width of bearing is 400 mm, carriageway width is given 7.5 meter, footpath 1 meter on either side. The curve dimensions are 600 mm wide and 300 mm deep. Wearing cord thickness is given 80 mm. Live load considered here is IRC class A drag vehicle. The materials used: M40 grade of concrete and 7 mm diameter high tensile wires with an ultimate tensile strength of 1500 Newton per mm square, housed in cables with 12 wires and encouraged by freshenet anchorage of 150 mm diameter. And Fe415 grade of steel is adopted for supplementary reinforcement. The compressive strength of concrete at transfer is given 35 Newton per mm square. The loss ratio is 0.8, and the codes referred here are IRC 6, IRC 112 and IS 1343. So now coming to step 1. So first we have to find out the maximum permissible stresses in concrete and steel following IS 1343 2012. So for this problem, we have assumed that the permissible compressive stress at transfer considering zone 1 is 15 Newton per mm square, which is denoted as FCT. And the permissible compressive stress at service load, which is denoted as FCW, is taken as 12 Newton per mm square. So these values we have assumed, and the assumed values, it should be within the permissible limits specified in the code. So now coming to the code, so this is your IS 1343. So you can see here this figure 7, figure 7, this is the permissible compressive stress values in service load, and this figure 8, this shows the permissible compressive stress values at transfer. So this first figure, this is for post tension work, and the second figure is for pre-tension work. So here the corresponding values for M30 grade of concrete is given. For zone 1 it is 0.41 FCK, and the corresponding permissible limit for M60 grade of concrete is given 0.35 FCK. So in our case we have used M40 grade of concrete, so it may be here, this is M50, then it will be here. So from if we draw here, so we need this value, so from the similarity of triangle, if we consider these two triangle, this one and this big one, so from these two triangle, if we consider the similarity, then you can find this value. So that will be nearly this first figure, figure 7, is for service load, which is a function of FCK. This is 0.39 FCK, which is coming 15.6 Newton per mm square. So which is more than the permissible value of compressive stress at service that we have taken, 12 Newton per mm square. Similarly, the permissible compressive stress at transfer for our case, the FCI value is 35. So here For M30 it is 0.54 FCI. For M60 it is 0.37 FCI. So this will be M40. This is M50. So this value, we need this value, corresponding will be here. So from this two triangle, this is one, this small triangle. For similarity of this two triangle, we can find out this value, which is coming to be 0.05 FCI, that is equal to 17.5 Newton per mm square. Okay. So next, what is the permissible tensile stress? Since we have taken class 1 type, so it will be 0. So here FTT is the permissible tensile stress value at transfer. So this T, the first T stands for transfer, second T, your first T stands for tensile, second T stands for transfer. Similarly, the FTW value, that is your permissible tensile stress at service, is also taken as 0. The ultimate tensile strength of 12 wires of 7 mm diameter high tensile cables, that is FP, this is given 1500 Newton per mm square. The maximum permissible stress in the high tensile cable is given 1200 Newton per mm square. The next step is calculation of depth of span. So by assuming the thickness of span at a rate of 50 mm, per meter of span, the overall depth is calculated as 50 into your span length, that is equal to 10. So total we got 500 mm. So if we use effective cover of 55 mm, then the effective depth will be the total overall depth minus effective cover, that is equal to 445 mm. Next, calculation of effective span. So in this question, the width of bearing is given 400 mm. The effective span is the minimum of clear span plus effective depth and the center to center distance between the bearings. So by calculating these two values, the minimum value is coming to be 10.4 meter. So this is the cross section of the deck slab. Total depth is 500 mm. Then your wiring cord thickness is 80 mm. Carriage over 7.5 meter. So next is calculation of dead load bending moment. Self weight of the slab is given by unit weight of reinforced concrete, that is 24 multiplied with the your thickness of the slab, that is 0.5 meter, that is 12 kilonewton per meter square, and the self weight of wiring cord is your thickness of the wiring cord, that is 0.08 meter into unit weight of wiring cord, that is 22 kilonewton per meter cube for bitumen. So this is coming 1.76 kilonewton per meter square. So total dead load, it can be obtained by adding this 2, that is 13.76 kilonewton per meter square. Now we can calculate the dead load bending moment, that is WL square by 8. Length is, the effective span is 10.4 meter. So we got this value 186.04 kilonewton meter as the dead load bending moment MD. Now calculation of live load bending moment. So to get the maximum bending moment, we have to place the live load on the span so that the bending moment will be maximum. So here we have to place the live load or the vehicle in the middle of the span. Now, to calculate the bending moment due to live load, we need to find out the uh, dispersion of load along both width and length. So what is the effective length of load that can be calculated by following the formula given in IRC 6 that we have already discussed in design of slab culvert, that is your 3.6. 3.6 is the wheel 3.6. This is the wheel contact area along the span plus 2 times thickness of uh, the slab plus the thickness of wearing cord. So this is coming to be 4.76 meter. Now the effective width of slab perpendicular to the span, which is given by the formula B is equal to kx 1 minus x by L plus bw. This is also given in IRC 6 that we have already discussed, and x is the distance from the center of the live load to the edge. So for this case, this is 10.4 by 2, that is 5.2 meter, length is 10.4 meter, width is 9.5 meter. So to calculate this k value, we need this ratio B by L, which is coming to be 0.913. So from IRC 6, there is a table for this k value which is coming 2.37 for corresponding value of 0.913. So by putting all these values in the expression for BE, we got the value of BA is equal to 7.172 meter. Now from this figure you can observe that if this is the vehicle is placed perpendicular to the span, so this is 850. This is the width of the wheel perpendicular to the span, and 1200 is the distance between the two wheel, and this is C value, that is 1200, and this is 1 meter, which is given in the question footpath. So as we got the dispersion of load perpendicular to the span, we have calculated 7.172 meter for a single wheel. So you can see from this figure, if from here to here the value is 7.172 meter, so half of this from the center of the wheel, this width is 7.172 by 2 meter, and from the distance between the two wheel irrespective of the dispersive width is how much? 1200 plus 850 by 2, 1200 plus this 1200 plus 850 by 2 plus 850 by 2, which is coming to be 2050 mm. And the rest part on the left side, which can be calculated. So this is 850 by 2 plus 1200 plus 1 meter, which is coming to be 2625 mm. So the net effective width of dispersion is 8261 mm by combining 2625 plus 2050 plus 7172 by 2. So we got the net effective width of dispersion 8261 mm. And as we know, for IRC class A tracked vehicle, for two tracks, the total load is 700 kilonewton. And if you consider the impact factor, which is coming to be 1.21 for span of 10.4 meters. So this impact factor value, this can be calculated by following the recommendations given in IRC 6, which is for a span of 5 meter, your impact factor value is 25%, and for a span of 9 meter, this is 10%. So for our case, the span length is 10.4 meter, so we can take the value of 10%. So your impact factor value is 1.21. 1. The average intensity of load including the effect of impact, 700 into 1.2 divided by the area of dispersive load, that is calculated the 4.76 along the span length and 8.261 perpendicular to the span length. So the total intensity of load considering the effect of impact, we got 19.58 kilonewton per meter square. Now we can calculate the maximum bending moment due to live load, that is your ml. So if so in this figure you can observe here, if VA and VB are the shear forces, so it will be the loading is 19.58, so 19.58 kilonewton per meter square into the width of vehicle is 4.76. so since it is symmetrical, so the shear force will be 19.58 into 4.76 by 2. So maximum bending moment due to live load ml is equal to the moment, positive moment due to the shear force, that is 19.58. This is 19.58 into distance, sorry, so this shear force value is 19.58 into 4.76 by 2. This is the shear force, that is VA, into the length from the center, that is 5.2, minus, this is the positive bending moment, minus the moment due to the vehicle load, that is clockwise. So minus 19.58 into 4.76 by 2 into 4.76 by 4. So this is coming to be 186.87 kilonewton meter. Next is your calculation of shear force due to live load and dead load. So to calculate, so to get the maximum shear force, we have to place the vehicles at the support. If you are placing the vehicle at the support, then again you have to find out the net effective width of dispersion. So you can see from this figure, so here only change will be the value of x. It will be from the center of the vehicle to the support, which is equal to 4.76 by 2. 4.76 by 2, that is 2.38, and all other values like k, bw, x, l, everything will be constant, as we have already calculated this effective width perpendicular to the span here. So all the values will be constant except x value, which is 2.38. so after calculating, we got this effective width value is 5.36 meter. So again, if you place the vehicle perpendicular to the span, then if we consider the overlapping of the loads here, so this will be how much? 5360 by 2, and this is 2050, and this is 2625. So combining all these three, we got 7.355 meter as the net effective width of dispersion. Now we can calculate the intensity of live load. It will be the total load, that is 700 into impact factor 1.1 divided by 4.76, that is the load dispersion along the span, that is already calculated, into the net effective width of dispersion, that is 7.355. So intensity of live load for calculation of shear, we got 22 kilonewton per meter square. So now we can calculate the live load shear force, that is equal to 22 into 4.76 into 10.4 minus 2.38 by 10.4, that is equal to 80.75 kilonewton. Now the dead load shear force that we can calculate by using this formula WL by 2. So dead load already is calculated, 13.76 into 10.4 by 2, that is 71.55 kilonewton. So now we have calculated the live load, the shear force due to live load, shear force due to dead load, then maximum bending moment due to live load, then maximum bending moment due to dead load. So next step is we will check the section for minimum section modulus. So these are the moment values. The dead load moment is 186.04 kilonewton meter. Live load moment is 186.87 kilonewton meter. Then the section modulus for rectangular section is BD square by 6, that is equal to 1000, as we are designing the section for 1 meter of width. So width is constant, that is equal to 1 meter into depth is 500 divided by 6. So the section modulus we got 41.67 into 10 to the power 6 mm cube. The permissible stresses in concrete, as we have already assumed, FCT value is 15 Newton per mm square, FCW is 12 Newton per mm square, FTW and FTT is taken as 0, and the loss is given 80%, that is 0.8. The FBR value is expression of FBR, that is eta FCT minus FTW. So eta is 0.8, FCT 15 minus FTW is 0. So the value of FBR we got 12 Newton per mm square. The expression of minimum section modulus is, it should be more than mn plus 1 minus eta md divided by FBR. So if you put all the values here, we got a value of 18.67 into 10 to the power 6, which is less than the calculated value, that is 41.67 into 10 to the power 6. So the selected section is adequate to resist the service loads without exceeding the permissible stresses. So we'll continue this design problem in the next lecture.